All right. So the equation that I got for system response, it's kind of long equation. It's hard to interpret. Uh, it's hard to get insights about the system and how does the system behave under different uh, variations or different conditions, forces, what happens if the natural frequency or damped natural frequency changes in a specific way with respect to the excitation frequency, what happens if the damping changes. This equation doesn't really tell us that much. Right? It can tell us what the system response is and wherever this it can tell us where this mass is at any given time, as long as we can find all the coefficients. uh, let's just make it a little more, I would say, easy to interpret and to get insights from. So what I'm going to do in order to achieve that goal, I'm going to define a couple of things, right? I'm going to define two things specifically. I'm going to define frequency ratio and another thing that's called static deflection. So let me just define these. I'm going to define frequency ratio, and I call it R. Let me write it this way. And let's just put them both. Frequency ratio, which is pretty much the ratio between the excitation frequency, frequency of the excitation force, and the natural frequency. And I'll call this, maybe I should do a better job in this, R. I represent that with R is equal to omega over omega n. And the second thing is a static deflection, or let's just call it static deflection. Static deflection. Show that with delta ST. And this is pretty much the deflection under the static force F naught. Right? We have F naught cosine omega t applied to our system. It's a dynamic force, obviously it's harmonic, but imagine that we just apply a static force F naught. How much this system is going to deflect, or it's going to move away from its equilibrium point, if you want to think about the spring mass damper system. So I define that as F naught over K. You can write it as deflection under the static force F naught. So if I do this, and what I'm doing now is that I'm just going to safely ignore the transient response. As I said before, that when we do design and when we look at the way the system reacts to different types of external force, in this case a harmonic force, we care about the steady state response mostly. It's good to check the transient response and make sure the amplitude is not that high, but we mainly look at the steady state response because that's the response that lasts for a long time, and that's the response that the system is going to have towards your external force. Right? So I will use that to redefine, use these two newly defined variables to rewrite x. So x, and x being the amplitude, I'm going to go back to remind you that x is the amplitude. X is x cosine omega t plus theta. Right? The x value is the amplitude related to the steady state response. So I'm ignoring the transient response, focus on the steady state response, and I'm mainly focused on what is the amplitude of that response. Remember, cosine omega t plus theta, whatever it is going to change from -1 to 1. Right? That's not a big, that's not something that goes out of that range. What matters the most is how that x value changes, and that's going to define the amplitude of this system response. So x, using these two newly defined terms, x becomes, I can rewrite x as, let me write it this way, x over delta st. Right? I'm just moving things around. I can actually write x first, so it's probably easier to follow. X is f naught over omega n squared minus omega squared 2 zeta omega n omega squared. So x is f naught over square root of omega n squared minus omega squared, right? And from there, well, I don't know if we got squared plus 2 zeta omega n omega squared. Now, using these two new definitions, I can rewrite this. I just ignore the details. You can just try this yourself, or you can just do the reverse process and go from what I give you to see you can actually get x in the form that we defined x at the beginning in the first place. So define x as x over delta st, static deflection, is 1 over square root of 1 minus r squared squared plus 2 zeta r squared. I skipped a couple of steps. Now this x over static deflection, right, I call this m. And this m actually has a meaning, or has a definition, or better say has a name. It has multiple names, but they all refer to the same concept. They call it magnification factor. Sometimes they call it amplification factor. And or you might even hear amplitude ratio, because it's the ratio between a dynamic to a static amplitude of the motion. It's trying to say that it's the ratio between x n omega squared, x omega n squared over f naught. Right? You move things around, you'll get that. Now, this is something we can focus on. This gives a more meaningful factor that we can take into account when we are doing design. It's the amplitude ratio, so it tells us, it gives us a good way of looking at the system. Now, as always, you know how much I love plots. As we say, plots are good because you can look at them and get the meanings out of whatever math we had to go through. System response, if you want to design something, usually plots are much more handy and useful than equations, because in so many cases we're looking at trends. Once we get the trend, we can always go back to the equations and get the exact number. Right. So let's take a look at how this magnification factor or amplitude ratio that I did put an extra n there, amplitude ratio change. Remember, this R is frequency ratio I put there. So I plotted this M, amplitude ratio, and the other factor that in a system, that in response, in our steady state response, which is theta. So two things I want to look at. How does M change, which M is a representation of X, but in a normalized way, so ratio of the magnitude. And how does theta change? Theta is also shows the phase difference between the force and the response. Now, I plotted these two. I'm going to bring them here as a function of damping ratio. All right, as I said, we want to see how things change when the damping change and when the frequencies change. Right? You want to get a good sense of how the system behavior changes under different conditions. So I plotted M and plotted theta. So this one is theta. Let me put it here. Actually, it's good to add vectors or axes here. So let me just add the axes there, right there, and this is also there. Not probably the best place to put that. There you go. This is theta, and the variation is, this is 0 degrees, this is 90 degrees, and this is all the way at the top, 180 degrees. I can do a better job than that. This is theta, and this is 180 degrees. This one here will represent M, right? Magnitude or amplitude ratio. X over static deflection. Now, let's see how things change. This is the kind of plot, these are the kind of plots you want to look at. We went from that complicated long equation, we said, well, we can safely ignore the transient response. I defined a couple of parameters so I could rewrite the system response, at least the steady state part of that. And I'm looking at how does that response, steady state response, which, remember, M is just a representation of X. Right? I just made it dimensionless by dividing that by delta S. Delta ST is a constant value. Right? It's just F naught over K. Right? For a given system, K is fixed. F naught is for a given system, for a given force, F naught is fixed. K is fixed, so F naught over K is just a fixed number. So this M is a pretty good representation of X, and it's a dimensionless number. And the theta, it shows that shows the phase difference. Now, let's see what conclusions you can make by looking at these plots. We're going to see similar plots later on about different types of systems, but this is the first set, or this is the first time you're exposed to these types of plots, the magnitudes and the phase. You will see similar types of plots when we talk about rotating unbalance and vibration absorbers. Here, let me also name the X axis. So this is frequency. That's a very ugly frequency. This is frequency ratio. Right? R equals to omega over omega n. So I'm plotting ratio R is equal to omega over omega n. I'm plotting theta and M as a function of frequency ratio. So starting from the first thing, that is something that to notice. If you have an undamped system, this is if you see these damping ratios values here. Right? The damping ratio starts from 0.1. Now, first thing to notice is 1, where we have frequency ratio of equal 1. That means omega is equal to omega n, right? R equal to 1 means omega over omega n is equal to 1, which means omega is equal to omega n. And that is what we know from before. This is resonance. That's where the resonance happens. Right? We defined resonance as, you remember when we were talking about spring mass system in a force vibration. Resonance is where the frequency of the excitation is equal to the natural frequency of the system. And you see that when we get close to the resonance, let's see if I plot that here, the amplitude goes up, which we actually saw that for a spring mass system. And the interesting part is the lower the damping ratio, which means less and less damping in the system, the higher the magnitude of the response close to resonance. And we know if there is no damping, the magnitude of the system response goes to infinity, goes all the way up. We saw that for a spring mass system when there was no damping. Even here, when we have damping, the lower the amount of damping, of course, we get closer to just a spring mass system. Our spring mass system is where the zeta is equal to 0. There's no damping. The magnitude goes higher and higher. So the first point I want to make is for an undamped system, in parentheses, where zeta is equal to 0. I didn't plot it here, but if you plot that, zeta equal to 0 would be something like this. I'll be all the way from there goes up. It goes to some very huge magnitude, almost infinity, theoretically speaking, infinity. So this is for zeta equals to 0. Since we have damping, it doesn't go to infinity in this system. But for an undamped system, the amplitude ratio goes to infinity as R goes to 1. What is R? Again, R is frequency ratio. When R gets close to 1, it means omega is getting very close to omega n, and we're getting close to resonance. Resonance occurs when there is no damping, goes all the way to infinity. We talked about this when we were talking spring mass system. Second observation that we see here is that the reduction in M, right, the magnitude or amplitude ratio here, in the presence of damping, pay attention to this sentence, the reduction in M in the presence of damping is very significant near the resonance. So when we are not close to resonance, again, the red line shows resonance. This is resonance. When we are not close to resonance and you increase damping, this is damping, right? This is zeta equals, it goes from 0.1 and then we increase zeta all the way to 3. It's overdamped system. We did this study for underdamped system, but I'm just increasing the damping so much and just want to know what happens. It becomes an overdamped system. So, and zeta is equal to 1 is critically damped. Okay, well, I introduced equations just for underdamped, but by just changing the damping, you will get a sense of, we want to get a sense of how the system behaves, even if it's critically damped or overdamped. So for critically damped system, we have zeta equals to 1. For overdamped system, I just use zeta equals to 3 as representative numbers for these two states. Now, if we look at these plots for the magnitude, we see that when we are close to resonance, somewhere around 1, or equals to 1 here, the amount of the reduction we see in M when we increase damping is huge. But when we go further, when we are closer to this side or when we are closer to this side, you don't see that much reduction in the magnitude or the amplitude of the system response when you increase damping. So the increasing the damping is most effective when you are closer to the resonance. Let me put that. The reduction in M, which is pretty much a good representative of the magnitude of steady state response, in M, let me put it this way, in the presence of damping is very significant at or near resonance. And by near resonance, I'm talking about where R is equal to 1 or close to where R equals to 1. You see, I'm mainly focused on the magnitude, the plot for the magnitude. But if you go here on the phase plot, you see by increasing the damping, I can see that, well, the phase also, the way the phase behaves change. For very underdamped system, very small value of zeta, you see that for low frequency ratio, somewhere around here, The phase is pretty small at the beginning and then slowly approaches 90 degrees. Theta approaches 90 degrees. And once we pass frequency ratio of 1 or we pass resonance, it goes above 90 degrees. Now, this change, the pattern or the way it changes, obviously changes depending on what the damping is. If for a damping equal to 0, if I want to put it here, theoretically, you will have something like this. That is for zeta equals to 0. Suddenly the phase switches, go from 0 degrees to 180 degrees. Keep in mind that at resonance, doesn't matter what you do with damping, has no effect on the phase. There is no lag in the system response. I'm not focused on the lag and system response here because you'll hear more about this when you probably, or if you take the control system theory. The way we control system, we care about the lag and lead and how does response relate to the force or external force applied to the system when we want to control the vibration or to control the system. Third thing is that the amplitude of vibration, right? We're talking about M here, representative of the amplitude. Let me erase this, clear things up here. The amplitude of the vibration becomes smaller when we increase the value of forcing frequency. What I'm trying to say, if we go to the right, that's where the omega, imagine you have a system, omega n is fixed, mass and stiffness is fixed, you're increasing the frequency of the excitation. So you're going to the right on the left plot, right? In both plots, you're going to the right. So if you increase the frequency of excitation, right, no matter what the system, what system you have, you're going to get farther and farther away from resonance, and the amplitude decreases. Right? So let me phrase it this way. The amplitude of the forced response or the forced vibration, and we just take steady state response as the response of the system under forced vibration, since we can again safely ignore in most cases the transient response. Forced vibration becomes smaller with increasing values of forcing frequency or excitation frequency. So what this trying to say, it says M approaches to 0. Right? You see M is going lower and lower, smaller and smaller, going down as R goes to infinity. You increase R by increasing the excitation frequency, and when R is increased, M is decreased.